Okay, thank you, Alpar. Thank you for the introduction, and good morning and good afternoon, everyone. First, let me thank the organizers for their very kind invitation and the opportunity to give this talk. So this is a joint work with Alessandro Goffi, who is a postdoc at the University of Padova. So since many things are quite unusual these days, and I usually prepare some BMAP presentation, I decided to make an exception. And today the problem I would like to address is quite easy to formulate, and I would like to show you some key ideas of the proof and some key computations. So I will try to use the blackboard or, okay, the whiteboard in this case. So roughly speaking, the problem I would like to address, again, can be written in a very single line. So we have a function which is defined on a domain of Rd with values in R. And we know that minus the Laplacian of u plus the gradient of u to some power gamma is in some Lebesgue space LQ. So this is something that we know, and we would like to prove that both the Laplacian and the gradient of u to the power gamma are in LQ. So here gamma is something which is bigger than 1, so we have a superlinear problem, and q is again some exponent bigger than 1. So you have basically this maximal regularity problem, which states that you have two pieces of an equation whose sum gives an overall LQ regularity, and you would like to understand the regularity of the two pieces, and you would like to get optimal regularity, the best that you can. But in this case is both the Laplacian and the gradient to the power gamma, so the Hamiltonian, let's call it, in LQ. So there is no weird compensation effect between two rough things that give, in the end, a nice outcome. The outcome is really a result of two regular pieces. So this is our maximal regularity problem that actually I will try to prove in the following way. So let me state it a little bit more precisely. So we are assuming that, again, U is a smooth solution of a Hamilton-Jacobi equation, which is of this form, the power gamma equal to F. So we have a right-hand side f of x. We assume that the LQ norm of the right-hand side is bounded by a constant m. And we would like to show that there exists a constant capital K, let's say. So there exists a constant capital K that will depend on everything. Okay, so on M, on gamma, on Q, on the space dimension V, and maybe also on the domain that we are working on, such that both the Laplacian of U, LQ norm, and the gradient of U to the power gamma, LQ norm, is bounded by K. Okay, so this is the problem that I will be addressing throughout this talk. And let me call it capital M. All right, so what are the motivations? So why considering this regularity problem, this PDE problem? Motivations, of course, the first thing would be stochastic control. Okay, stochastic control. Of course, this, as you know very well, this equation, this Hamilton-Jacobi equation, arises in the study of ergodic or long-time behavior or of control problems in a stochastic setting. Actually, this equation appears also in a quite different circumstances, like the theory of growth of surfaces. And in that community, this equation with kind of different signs is called the Kardar-Parisi-Zhang equation. So let me also mention the KDP equation. Now, of course, another motivation here is mean field gains. Okay, so if you would like to study a mean field gain in the ergodic setting, so in the stationary setting again, so with the form of minus Laplacian of u plus h Hamiltonian of x gradient of u equals to f So with the local coupling, so with the coupling with the Fokker-Planck, which depends on the density of the measure, and so coupled with the Kolmogorov-Fokker-Planck equation, this form, usual one. Well, here, of course, you are facing this kind of regularity issues. If you want to prove existence of solutions, and imagine that your Hamiltonian is again behaving like a power of the gradient with superlinear nature, and the coupling is as well something which is of power-like nature, then you are suddenly in the position to try to get estimates if you want to prove some existent theorem, for example. And when you want to prove estimates, you want to really understand the regularity of the two equations. Okay, so typically, a typical plan would be you start from something, so you start from some information on the right-hand side of the Hamilton-Jacobi equation, like F is in some LQ, and you would like the first equation to regularize, or at least to preserve some regularity, okay? So to set up, in the end, the bootstrap procedure. If your equation is not giving you regularity, or even worse, if it is destroying regularity, so if you do not have this kind of maximal regularity thing, then probably you are starting from, not starting from the good point. You should start from a different level of regularity to set up a bootstrap. Okay, so a third motivation, and this was kind of challenging for us, but it was really motivating. This is something that Pierre-Louis Lyons discussed for a couple of years during several seminars, and actually he made a very, very precise conjecture. So Pierre-Louis Lyons' conjecture is maximal regularity holds. So this kind of maximal regularity thing holds if and only if Q is bigger than V times gamma minus 1 over gamma. So I recall you, Q is the, let's say, the back class of the right-hand side. V is the space dimension, gamma is the growth of the Hamiltonian. And he says, okay, we expect this result whenever Q is bigger than this coefficient that, for simplicity, I will call Q bar. Okay, so Q bar, it is this threshold starting from which we expect this kind of maximal regularity. So let me say something about the literature. And well, the literature regarding semi-linear and quasi-linear equations is so huge that it would be impossible for me to make a full list of contributions. But let me just try to say something about the tools and the techniques that are around. So I think we should go back and we should start from some pioneering works. We have pioneering works by Cirant, by the group of Ledizhenskaya. So Ledizhenskaya, Uraltseva, etc. We have Aman Crandall, contributions by Aman Crandall. Lyons himself. So here we are starting from the 60s and 70s, and these are really the main starting works on the regularity for this kind of Hamilton-Jacobi, or in a wider framework of semilinear and quasi-linear equations. So many results here are for the case gamma less than 2. So are for the case in which the Hamiltonian is growing in a subquadratic way. Okay, so the growth of the Hamiltonian is controlled by quadratic exponent. Then there is the very important chapter of viscosity solutions. These are methods that are based on a maximum principle, very powerful. But here, unfortunately, we should require, in order to apply these methods, f, so the right-hand side of the equation, to be continuous or even Lipschitz. Okay, so they're very powerful tools, but in our case, not really useful because of too much regularity required. We are working at a lower level of regularity. So we go to the realm of techniques involving weak solutions. Okay, so we have a very important branch of research of methods involving weak solutions. Here, I should mention a lot of names: Lucio Boccardo, Puel, Murat, a lot of people. Again, most of them restrict to the case gamma less than 2. On the other hand, they can work at very low level of regularity, so they typically deal with something which is involving the Hamiltonian, so the gradient of u to the power gamma in L1. And the good thing is that they can deal also with very weak right-hand sides like f in L1 or even measures. Okay, so these are very powerful tools as well, but not really helpful in our situation, because in some sense, our problem lies in between, okay, as we'll see in a second. Let me mention also something that have been developed also by Italian people from Naples, so method involving symmetrization techniques. And I put this line in the, let's say, world of weak solutions. And there is also a very active and productive field, which is the one of nonlinear potential theory. They have very powerful methods as well. They can work at very fine and delicate levels of regularity, and they can break quite easily the threshold of quadratic growth with respect to Hamiltonian. They can work in the full superlinear scale. Here, people that contributed are Mazia and very recently Nguyen and Puk. So let me say something about what Lyons said about this problem. So Lyons mentioned, again, discussed this conjecture in a series of seminars, especially during 2012, 14, 13, etc. This was somehow the period. And he discussed how to actually prove this conjecture in particular cases. So one particular case is the case of quadratic growth, is a special case of dimension 1, and special case of gamma, which is close to 1, so superlinear, but not too much superlinear. And he proposed actually modifying one of his old results, how to attack the case where Q is below the space dimension, but still bigger than some constant, which is not achieving the optimal one. So he has some results, and he discussed how to prove it. But still, the conjecture has remained open in full generality. So I have also to mention duality methods. Duality, the idea of duality go back, I think, in the ancient times, but it was Craig Evans that revived it in the nonlinear framework, and many people also, I think, among the audience here contributed in this direction. So about duality methods applied to this problem, Alessandro will talk about that in the forthcoming talk. Okay, let me say a few words about. You see, I've written a couple of times gamma less than 2. So why gamma less than 2 is important in our problem? Gamma equal to 2 is important, and it is called natural growth. When gamma is bigger than 2 and you enter into the unnatural growth, many techniques break down. So this is a problem, and we would like to cover the full superlinear scale. So why natural growth? I could give you a certain number of motivations for this threshold, this quadratic threshold to be important. Let me just mention a few might be helpful to understand a little bit the problem. So the first thing is that if you perform an L-infinity scaling, so if you scale your problem and you zoom into small scales, so basically if you define a v of x, which is u of epsilon x, then if you write the equation solved by v, you realize that there is a minus epsilon to the power gamma minus 2. 2 minus gamma. Laplacian of v plus dv to the gamma equals to epsilon to the gamma f of epsilon x. So you see that when gamma is equal to 2, the two terms here behave in the same way, while if gamma is less than or bigger than 2, then one will dominate with respect to the other. And actually, when gamma is, okay, I think I was right. At the beginning it is gamma minus 2. So when gamma is less than 2 and you look at small scale, it will be the Laplacian, the dominant part. So the equation will be somehow linear in a sense, in a very rough sense. While if gamma is bigger than 2, then you should really be careful about the gradient part, because that will be the dominating part in some sense. Now, another situation in which the quadratic growth is important is the following. So suppose for a second that your right-hand side of the Hamilton-Jacobi equation is 0 and you are exactly in the quadratic case. Now, you do another change of variables, so you define u to be some function phi of v. Well, what is the equation satisfied by v? Well, it will be something like minus Laplacian of v plus some stuff involving derivatives of phi times the gradient of v square equal to 0. So first observation, the quadratic structure is preserved via the chain rule. Okay, so this is not working with different Hamiltonians. It's a property of quadratic Hamiltonian. And if you choose, if you make a choice for phi to be the logarithm, so if u is actually the logarithm of v, which is the well-known Hopf-Kohl transformation, well, you basically get rid of a piece of the equation. So this is becoming 0 with this choice. And you are left with a much more simple equation, a much simpler equation you can deal with. And actually, this is the way that Pierre-Louis Lyons proved the maximal regularity in the case gamma equal to 2. When gamma is equal to 2, you can simplify a lot the problem with the Hopf-Kohl transformation, and you get the result, applying some standard stuff in linear equations like Harnack and some Aronson-Senring result. So this is about the natural growth. Now let me say a few words about this critical exponent, the critical exponent who's entering into our problem. So this is really related to the nonlinear nature of the equation. And again, let me try to convince you that this is the crucial exponent. So a first way to observe this criticality is to perform another scaling of the equation. So you define w of x to be epsilon to the power 2 minus gamma over gamma minus 1 u epsilon of x. So why this rescaling? With this rescaling, the full structure of the equation is preserved, so both the linear and the Hamiltonian part. And you get dw to the gamma equals to epsilon gamma over gamma minus 1 f of epsilon x. Now, just give a name to this rescaled right-hand side, and you realize that this scaling that preserves the equation preserves also the LQ norm of the single pieces of the equation. So, for example, if you want to evaluate the LQ norm of the rescaled right-hand side, well, this will be invariant, so it will not vary with respect to epsilon, if and only if Q is equal to Q bar. So this is really the scaling that you have a look, this is really the Lebesgue scale that is preserved under this rescaling that preserves the equation as well. So another viewpoint, of course, everything is related, but let me try to give you a different viewpoint on this critical exponent, and which sheds also some light on the difficulties of the problem as well. So for a second, consider the equation in some sense as a linear equation. So write minus Laplacian of u as minus the u to the power gamma plus f. Now, the fact that I write this way, in some sense, enables me to use the so-called elliptic regularity. So elliptic regularity says that if your Laplacian is equal to something, well, you will be able to gain two derivatives, regularity in two derivatives. So what do I mean? What do I mean? I mean that we can control the Hessian in an LQ space by the LQ norm of the right-hand side, okay? So we can control it by the LQ norm of the u to the power gamma plus the LQ norm of f. Now here on the right-hand side, we put the gamma outside, so we have the u LQ gamma to the power gamma, and on the left-hand side, so you see we have a gain in terms of regularity. We start from the gradient and we reach the Hessian. Now with the Sobolev embedding, we can say something related to the gradient back again, so we can control the gradient of u in LQ star, where Q star is the Sobolev exponent QD over D minus Q. So we have a gain now in regularity whenever Q star is bigger than Q gamma. So your equation regularizes at the level of the gradient in the Lebesgue spaces whenever Q star is bigger than Q times gamma. But this is true if and only if, to the computations, Q is bigger than our critical exponent Q bar. So this is what I was saying at the beginning. We would like the equation to regularize. Well, it's completely natural to for the equation to regularize when Q is bigger than this threshold Q bar. Okay, and there is another thing that I would like to point out in this computation. Okay, here it seems that everything is okay, but here we have a exponent gamma in the right-hand side. So we have actually an estimate that doesn't say anything if you don't know anything about this quantity. Okay, so if you would like to close things, well, it's difficult because this is highlighting in some sense the superlinear nature of the problem. This gamma on the right-hand side is saying that the right-hand side is growing very, very quickly with respect to the left-hand side. And this is a problem when you try to use this argument that I just sketched you, okay, to you. Okay, another preliminary comment about this threshold. Well, Lyons has very good reasons for claiming that, for saying that this result is false for Q less than Q bar. Well, because there is a counterexample. So when Q is less than Q bar, you do not expect this result to be true. This result is not true in general. And the construction of the counterexample is very simple. Very simple because you just have to take a function u, which is some constant, suitable constant c, times x to power gamma minus 2 over gamma minus 1. Gamma minus 2 is again a special case, but anyway, what's special about this solution, this function? Well, this is a solution of minus Laplacian of u plus du to the power gamma equals to 0. And you see immediately that there is some bad things around, because of course, okay, so this will be in a weak sense. And here, the bad thing is that you have a very nice right-hand side, very smooth right-hand side, and okay, maybe smooth, but not so much, so it will be Holder or even unbounded if gamma is less than 2. So actually, what happens here is that the gradient u to the power gamma is in LQ, but Q is actually less than Q bar. So why is this a counterexample? It is not really a counterexample of the conjecture, because I said, okay, I would like to prove an a priori estimate. And this is just a weak solution of an equation, so it's not something that we would like to deal with. But if you, this solution is singular in the origin, okay? So if you remove the singularity with the truncation, so if you define the epsilon to be a truncation, let's say the epsilon times u, and if you choose key appropriately, then you have the minus Laplacian of v epsilon plus the v epsilon to the power gamma is equal to some remainder f epsilon that will vanish almost everywhere, let's say, when epsilon goes to 0. But but choosing appropriately, again, the function chi will lead to a sequence of v epsilon such that their norm, I'm sorry, this is dv epsilon to the power gamma. So what we would like to estimate, what we would like to be bounded, will go to plus infinity as epsilon goes to 0, while the right-hand side of the equation will stay bounded as epsilon varies. So we see that if we work at this level of LQ regularity, the equation is not helping that much, because we have a right-hand side, again, that is stable in LQ bar, so at the threshold, but we have two pieces that separately will explode in the LQ bar norm. Okay, so this is what we don't want. Okay, so the question is, can we prove that this conjecture, so this regularity, holds for Q bigger than Q bar? Well, yes. Yes, we have to add a little assumption. So we can prove this conjecture, but we have to require this exponent Q to be bigger than 2. Okay, so let me sketch a picture. Probably it's better to sketch something to clarify a little bit which cases are we able to treat. So if we draw the exponent Q bar is a function of d and gamma. Okay, so suppose that, d is fixed, and let's try to draw the value of Q bar. Well, Q bar will go something like this, and we'll approach d as gamma goes to infinity. So I've just showed you that if Q is less than Q bar, we do not have the result. So here, I mean, the conjecture, the maximal regularity doesn't hold. So here we know that this is false. And so we are able to prove that the result is true if Q is bigger than Q bar and bigger than 2. So we have to suppose that Q is bigger than 2, and we have the proof here. And we are basically left with two small regions that is here. So Q less than 2, but bigger than Q bar. And so here we have a question mark. And actually, I will come back to this in the end if I have 1 second. Actually, also the threshold is not clear, not completely clear what to expect. But I come back to this later. So let me try to say something about the proof. Okay. and I apologize because the proof will be quite technical. I mean, it's quite technical, and I will really try to highlight the main ideas, the main key things that that worked. So the proof is via the good old Bernstein method. Bernstein, because here again we have a nonlinear part, which is the gradient to the power gamma. So we have a coercive term in the Hamiltonian, and we have an elliptic, we have a Laplacian. And we would like both things to help in the regularity. So we cannot really treat the equation as a perturbation of the Laplacian or as a perturbation of the Hamiltonian. We really have to squeeze out everything possible. Okay, so Bernstein is a way. Bernstein is a way. So what is Bernstein? Okay, Bernstein, it says that, okay, you want to study the gradient regularity, so consider an equation for the gradient. So consider a linearization of the equation. Look at the equation at the level of derivatives. In other words, so the original idea was actually to have a look at the equation solved by gradient to the power u, to the square. And actually here we work with the, here I'm cheating a little bit, but I will work with an equation for the absolute value of the gradient, okay? So I recall you the equation is minus Laplacian of u plus v to the power gamma equals to f, basically, because v is the absolute value of the gradient. And so you differentiate the equation, and you get something for v. So this something for v is the following. You have minus Laplacian of v. You have the linearization of v to the power gamma, so v to the power, let's say, gamma minus 1 dv. Okay. And then you have something that comes from a uniform ellipticity, which is very important. And I draw it in blue, which is a term involving the second derivatives, so the full Hessian, the power 2, okay, times v to the minus 1, because we are looking at the power 1 of the gradient, equals to df times du over v. Now, a very nice trick that is known in the field is now to plug back the equation in this equation for v. What I want to say is the following. Here you have the full Hessian, okay, and so you have in particular the Laplacian. So here you have a Laplacian of u plus positive things, okay, but you have the full Laplacian to the power 2. And so going back to the equation, what you have here, you have v to the power 2 gamma, because you have the Hamiltonian, plus f to the power 2. So let me arrange a little bit. Once you realize that you can plug back the equation for u in the equation for the gradient, well, in this way, you can highlight some coercivity, some very strong coercivity with respect to the gradient itself. So you have a v to the power 2 gamma minus 1. So this is the regularizing part of the equation. And on the right-hand side, I put the stuff that we would like to estimate. So we have, let's say, of course, I'm skipping every constant. For simplicity, this is a very rough computation. You have the f, and this is multiplied by a bounded term, so I'm skipping. So now at this point, well, v is the thing you would like to bound, and at this point, a very natural way to proceed would be to do some weak method, okay, to get regularity. And by weak method, I just mean test the equation by the right suitable power of v itself. So v to the power beta, b to be chosen. Okay, so you do that, integrate on your domain. By the way, I haven't said anything about the domain, but for simplicity, let's suppose that everything is periodic. So we are working on a unit cube. So every time that we integrate, so no boundary conditions. This is quite okay in at least part of the literature of mean field games that deal with periodic boundary conditions. It might be completely unnatural, but just for simplicity, suppose that everything is periodic and suppose that there is no boundary effect. So test the equation against the v to the power beta, and you have beta integral of v beta minus 1 to the times dv to the power 2. This is the elliptic part. And then you have the coercive term, which is v to gamma minus 1 times v beta, and then you have the right-hand side. So it's, let's say, less than or equal to integral of v to the power gamma minus 1 plus beta dv, plus all the stuff involving f. So, and I'm not saying anything about f. So it's a matter of time. So just let me try to focus on a problem. So the problem is that now you would like to balance this term in the right-hand side with the things that you have on the left-hand side. And there is only one way to apply Young inequality. With Young inequality, you have a gradient, you can raise it to the power 2, and you get, let's say, epsilon v to the power beta minus 1 dv square, so exactly what you have on the left-hand side. But what you're left with is 1 over epsilon v to the power 2 gamma minus 1, plus beta. So whatever your choice, whatever you choose for beta, you will always lose. Because you balance the first term, but you're not able to balance the second term. So up to now, everything was known. Okay, so this is a method that was developed, for example, by Pierre-Louis Léonce himself in an old paper, 1985. But at this point, you are stuck unless you require beta to be large. Okay, you can play with this beta large, so you will be able to get some result, and I think this is the results that he's able to get by playing this beta large. But if you choose beta large, then you lose something. Okay, you cannot prove the result in full generality. So the first key idea is the following. To overcome this difficulty is the following. So to push a little bit further this Bernstein method is the following. Instead of looking at the equation for the, let's say, full gradient, you just focus on sets where the gradient is large. In other words, you go back to your definition of V, and you subtract some big constant and take the positive part. This is also a very classical method, very classical idea, Stampacchi, etc. So K with K big. What's changing? So the equation is basically the same. So you get rid of the part of the equation where the gradient is small, let's say. You are left with the Laplacian of Vk. The coercive term is not touched. Okay. You have Vk here, and you test again Vk. Okay. Now, what you gain with this method. So this is Vk. This is Vk. What you gain by this method is that when you perform again this Young inequality on the right-hand side to control it, well, here you have all the Vks, but now if you track everything, here you do not have exactly what you have on the left-hand side, because you have Vk to the power 2 gamma minus 2. So this is V times Vk to the power beta minus 1. So you are starting to have a little bit of asymmetry. Okay, so there is some room. You see here you have V to the power 2 gamma minus 1. I mean, this is technical, but this is the point. V to the power 2 gamma minus 1, Vk power beta. And here you have power minus 2, and Vk to the power minus 1. And you observe that actually V is much larger in some sense, in very rough sense than Vk. So The trick here is that you can perform another Young inequality to control this by what you have on the left-hand side with the constant epsilon, so you can balance. So epsilon v to the power 2 gamma minus 1 vk beta, plus, okay, a remainder, which is big, but it contains only vk. So vk to the power 2 gamma minus 1 plus beta. So apparently you haven't gained that much. So apparently you're still in some bad position, but then you perform some classical things, Sobolev inequality, and you get and you get to that. You get to the integral. You arrive to the integral of vk, which is the thing that you would like to bound again, to the power q gamma with the appropriate choice of beta, to some power which is coming from Sobolev embedding, less than constant, so there are constants around, same quantity, vk to the power q gamma, with linear growth, plus a remainder. Since you are looking at super level sets of things, measures are going to 0, so with this remainder is going to 0 as k goes to infinity. Okay, so this is probably still not a very nice inequality. Apparently it doesn't say that much. So here we have the second main ingredient of the proof. How to use this inequality that is basically saying anything about vk, okay? Because we have here a smaller power on the left-hand side is smaller than the power 1 of the right-hand side. So how to use that? Here we are using a very nice and I think non-standard idea by Grenon, Murat, and Forretta. We have a superlinear problem, how to squeeze out, we have superlinear inequality, how to squeeze out something from that. So the idea is that you call yk, the thing you would like to bound, as yk varies. So you have yk to power d minus 2 over d less than yk plus remainder. And if you draw things, you have the sublinear part, which is on the left-hand side. You have the linear part on the right-hand side. So the inequality is not really saying anything. It is just saying that the quantity you would like to bound is either small or very big. Okay, so yk is either here or very big. So how to conclude? It might be very big. It cannot be very big. Why? Because the function yk as a function of k is continuous and it vanishes. Okay, yk goes to 0 as k goes to plus infinity. Now, you do not know in general, okay, you would like to quantify things, you would like to bound yk, you know that yk vanishes, so you know that for k large, yk has to be here in the bounded regime, okay? But since it is continuous, it's not just small when k is large, it has to be small for all k. So this is the key. So this is the key idea to use this superlinear inequality. And with this observation, you are able to conclude that the integral of, so yk is controlled for every k, and so as a consequence that the u to the power gamma is controlled. At some point, so to get this inequality, at some point we have to choose q. We have to assume that q is bigger than q bar. So it's hidden inside, but the threshold is appearing in the computations that I just showed you, and that's it, okay? And that's it. So I know that I have very few minutes, so I will just very quickly say a couple of things about applications to meaningful games. So I prepared something. So again, the problem I would like to address is a narcotic problem. So everything is set up to study regularity for this ergodic mean-field game, under the assumption that the right-hand side is growing as a power of the density m. So the idea is that well, again, you have to set up a bootstrap if you want to prove a priori estimates and then get resistance. One very natural way, is to use some structure of the system, so to use some energy inequality or to use some first order inequality. You can call it many ways. So you start from some information of M, which is an information basically on the right-hand side of the equation. And you, if your information is enough to have maximal regularity, so if the degree of integrability of the right-hand side starting from this information is enough to use the result of the maximal regularity, you start with the bootstrap procedure and you get some existent result. And what we get is an existent result under some growth restrictions with respect to the growth of the coupling. And this is in line with some previous results that I obtained with completely different methods. So a way to improve a little bit, so to have some more general results in this direction, is to use second order estimates, so to use a better information of the right-hand side of the equation solved by U. So here you start with a little bit more, and we have some new results on the existence of solutions in the local case for this ergodic mean-field game. I'm sorry, I was really fast on this, and I apologize. But the idea is that we are able to, with a lot of work, to improve a little bit the existing results that we have for mean-field game systems. So a couple of final remarks. We are able to make this estimate local. So it's not just on the torus. You can work on any domain, basically on balls. For example, we still have to address the case, the critical case. So when the degree of the integrability of the right-hand side is exactly at the critical Lebesgue class, critical Lebesgue space, I said that there is this counterexample. In general, it is false. The regularity, probably it can be proven, provided that the norm of the right-hand side is small. Okay, so probably this would be in line with other existence results that actually can touch the critical case. There is still open this small regime where Q is less than 2. We have some partial results, but still not a complete picture. And there is the parabolic problem, which is also very interesting. And the technique of Bernstein basically breaks down. And this is something that will be addressed. We have been working on that with Alessandro. We have a couple of results, and this will be the matter of the next talk by Alessandro. And with this, I thank you very much for your attention.